Most people have no idea they're saying it wrong. You've probably heard someone talk about cement floors, cement sidewalks, or cement trucks your whole life. But here's the twist. In most of those cases, they're actually talking about concrete. And while that might sound like a tiny detail, it's a bit like calling flour a cake. One is an ingredient. The other is the finished thing that holds up bridges, sidewalks, and skyscrapers. So today, we're finally clearing up the confusion once and for all. What's the real difference between cement and concrete, and why do so many people get it wrong? Cement is where it all begins. Think of it as the ultra-fine, super-reactive glue of the construction world. It starts its life as a mix of limestone, clay, and a few other minerals that are crushed and then heated in a gigantic rotating kiln at temperatures of around 1,450 degrees, hot enough to partially melt the rock. Inside that fiery tunnel, the raw materials chemically transform into hard nodules called clinker. Those nodules are then ground into a very fine powder and blended with a small amount of gypsum and other additives. That's what we know as Portland cement, the most common type of cement used worldwide. On its own, cement doesn't look like much, just a gray powder in a bag. If you mix it with water, it will harden into a brittle mass, but it's not something you'd want to build a bridge out of. It shrinks, it cracks, and it doesn't have the toughness needed to handle real-world loads. That's because cement isn't meant to work alone. It's a binder, a glue. Its real power shows up only when you give it something to hold together. That's where concrete enters the story. Concrete is the final, rock-solid material you walk on, drive on, or live inside. It's made by combining 4 key ingredients: cement, water, fine aggregate, like sand, and coarse aggregate, like gravel or crushed stone. When you mix them together, something remarkable happens. The water reacts chemically with the cement in a process called hydration. Tiny crystals begin to form and grow, locking the sand and stones together into a solid, stone-like mass. Over time, this mass gets harder and stronger, turning from a slushy gray mix into the sidewalk outside your house or the columns holding up a highway overpass. Here's a simple way to remember it. Cement is to concrete what flour is to cake. You wouldn't grab a spoonful of flour and call it cake. Flour is just one ingredient. You need sugar, eggs, butter, and heat to turn it into a dessert. In the same way, cement is just one part of the recipe. Only when you add water, sand, and gravel do you get concrete, the finished cake of the construction world. So if you're standing on a driveway, a road, or a bridge deck, you're almost definitely standing on concrete, not cement. So why do people mix up the terms so often? First, cement is the most famous ingredient in the mix. If you've ever seen a bag at the hardware store, it usually says Portland cement, and somewhere in our minds, that label sticks. We start calling anything gray and hard cement. Even on job sites, you'll hear workers say things like pour the cement or walk on the cement, even though they're technically talking about concrete. Language is lazy. Once a word sort of fits, people just keep using it. Branding also plays a big role. At the store, you'll see bags labeled cement mix or ready mix, and they sometimes already contain sand and small stones. To a casual shopper, that looks like one product: cement. In reality, some of these are closer to pre-made concrete in a bag. You just add water. The marketing doesn't always make that distinction clear. Over time, the lines blur, and people assume cement and concrete are interchangeable names for the same stuff. Now let's zoom in on what actually happens when cement meets water. When you pour water into a pile of dry cement, you're not just making mud. You're activating a complex chemical chain reaction. The compounds inside the cement, mainly calcium silicates, start reacting with the water to form microscopic needle-like crystals. These grow and interlock around the sand and gravel, filling in gaps and binding everything together. This is the hydration process. It starts as soon as water is added and continues for a long time, days, weeks, even years. That's why concrete doesn't just dry, it cures. Drying is about water evaporating. Curing is about chemical bonding. If concrete dries out too quickly, those reactions stop, and the result is weaker, crack-prone material. That's why you sometimes see freshly poured concrete being sprayed with water or covered with plastic sheets. Workers are not trying to get it dry faster. They're trying to keep enough moisture in so the cement can fully react and reach its design strength. This isn't a modern discovery. The idea of a cement-like binder goes back thousands of years. The ancient Romans developed a form of concrete using lime and volcanic ash called pozzolana. They mixed it with aggregates and even used it underwater. Structures like the Pantheon in Rome, with its massive unreinforced concrete dome, are still standing after nearly 2,000 years. Their cement wasn't Portland cement like we use today, but the principle was the same. A reactive powder plus water plus aggregates equals a durable stone-like material that can be shaped, poured, and molded before it hardens. Not all cement is created equal. While Portland cement is the everyday workhorse, engineers use different types to handle different conditions. There's sulfate-resistant cement for structures exposed to harsh soils or seawater, which helps prevent chemical attack. There's low-heat cement for massive pores like dams, where too much heat from the hydration reaction could cause cracking. There are also rapid hardening cements that gain strength quickly, useful for emergency repairs or projects that need to get traffic moving again as soon as possible. So when you hear cement, it might refer to a carefully engineered formula designed for a specific environment. Concrete itself also comes in a huge variety of forms. The plain gray slab you see on a sidewalk is just the beginning. Add steel bars or mesh inside, and you get reinforced concrete, strong in both compression and tension, perfect for beams, floors, and columns. Introduce tiny steel or synthetic fibers, and you get fiber-reinforced concrete, which helps resist cracking. Mix in tiny air bubbles, and you get air-entrained concrete that stands up better to freeze-thaw cycles in cold climates. There are lightweight concretes, high-strength concretes, decorative stamped concretes, and even translucent concretes that allow light to pass through. And then there's the sci-fi stuff, self-healing concrete. Some experimental mixes include bacteria or special chemicals that remain dormant inside the hardened concrete. When tiny cracks form and water seeps in, they wake up and start producing limestone or other minerals, slowly sealing the cracks. It's as if the concrete has a built-in repair system, extending its lifespan without human intervention. The basic ingredients are still cement, water, and aggregate, but the way we tweak them unlocks entirely new behaviors. Getting the proportions right is crucial. Too much water, and the concrete becomes easy to pour, but weak and porous once it hardens. Too little water, and it becomes stiff and difficult to work with, leaving voids and poor bonding. Builders often talk about the water-to-cement ratio, the amount of water compared to cement by weight. Keep that ratio low and controlled, and you get strong, durable concrete. Let it creep too high because a little extra water makes it easier, and you pay for it later with cracks, dusting surfaces, and early deterioration. Curing time matters too. Concrete doesn't reach its full strength in a day or even a week. A common benchmark is its 28-day strength, the value engineers use when designing structures. But even beyond that, concrete can continue gaining strength as hydration goes on. That's one reason massive structures like dams can keep curing internally for decades. Deep inside, where the heat and moisture are trapped, the cement keeps slowly reacting. It's also important to understand where cement shows up outside of concrete. Because it's such a strong binder, cement is used in mortar, the paste that holds bricks and blocks together. It's in many types of stucco, the plaster-like coating on exterior walls. It's in grout, the filler between tiles. In all of these, cement is acting as the glue that bonds sand and other fine materials into a solid skin or joint. But you still don't see buildings made out of only cement. Without aggregate, it's just not dimensionally stable or economical enough to be the main structural material. Concrete, on the other hand, is absolutely everywhere once you start paying attention. Roads and highways, sidewalks and curbs, parking garages, runways, dams, stadiums, skyscraper cores. Even wind turbine foundations and underwater tunnels rely on concrete. Massive projects like the Hoover Dam used millions of cubic meters of the stuff. It's one of the most widely used man-made materials on the planet, second only to water in terms of global consumption by volume. But there's a big downside to all this. Cement production is extremely energy intensive and produces a lot of carbon dioxide. When limestone is heated to make clinker, it releases CO2 both from the fuel burned and from the chemical breakdown of the rock itself. The cement industry alone is responsible for a significant percentage of global CO2 emissions. That's why researchers and companies around the world are racing to develop greener alternatives. Cements that use less clinker, blends that incorporate industrial byproducts like fly ash or slag, concretes that trap CO2 as they cure, and designs that simply use less material without sacrificing strength. We're also seeing futuristic techniques like 3D printed concrete, where robotic arms extrude layers of specially formulated concrete to build walls and structures with minimal waste. Ultra-high-performance concretes can be made so strong that beams and slabs can be slimmer and lighter, reducing the amount of material needed. All of this still depends on the same basic relationship: cement as the binding ingredient, concrete as the finished composite. So the next time someone points at a sidewalk and calls it cement, you'll know what's really going on. Cement is the gray powder, the binder, the glue. Concrete is the hardened mix of cement, water, sand, and stone that forms the physical world around us. One is an ingredient you truck in by the bag or ton. The other is the final product that holds up your house, your local bridge, and your favorite sports stadium. Understanding the difference isn't just about sounding smart at a hardware store. It's about appreciating the hidden systems and materials that shape modern life. Every time you drive on a road, walk through a parking garage, or stand beneath a towering building, you're trusting concrete. And inside it, the cement holding everything together. Now you not only know the difference, you can explain it to anyone who gets them mixed up. If you've got another everyday object or common phrase you've always wondered about, drop your question in the comments. We might feature it in a future episode and give you a shout out just like today. Don't forget to like, subscribe, and stay tuned for more stories hiding in the everyday details all around you.